All right, thank you everyone for being here. So this is the first of our two student speaker sessions. So we've got two student speakers today. First up is Teixeira. She's a second-year graduate student in the Department of Astronomy here at UT. She received a bachelor's in astrophysics and biology from the University of Florida, where she worked with Sarah Fowler to study the demographics of N4 exoplanets and implications for biological evolution. She now works with Caroline Morley, developing and using simulations to model the evolution of CO2-dominated terrestrial planet atmospheres. Broadly, she is interested in what makes planets habitable and how to search for both habitable and inhabited planets. Thank you.
Thank you for the introduction. So today I'm just going to be talking about some of the work that I've been doing over the past year and a half with Caroline Morley. So I've just been working on trying to use simulations to model these terrestrial exoplanet atmospheres through the main processes that we think affect atmospheres. And the planets that we're able to observe right now with the current technology are those that orbit M dwarfs. Oh crap, this is that's the right one. I'm sorry. So these are planets that orbit M dwarfs. So we are really interested in whether these planets are able to have atmospheres when they orbit M dwarfs, because M dwarfs are very different than sun-like stars that we think. So what they're different is they have much longer lifetimes. So each stage of their life is kind of stretched out. So they take a lot longer, so 1 to 2 gig years to reach the main sequence. And during this part of their lives, they're very active. So this is like a comparison between a very active young M dwarf compared to the sun, which is a lot older. So during this time, we think it might be very inhospitable to rocky planets that are possibly in the habitable zone or closer to their host star. And we also are kind of thinking about this from the perspective of the solar system. These are the planets that we know, and we know about their atmospheres, way more than we know anything about exoplanet rocky atmospheres. So, and what we've noticed is that, other than Mercury, which doesn't really have an atmosphere, and Earth, which is complicated, the other two rocky planets do have CO2 dominated atmospheres. So that's what we're really focused on. So we think that might be common in exoplanet systems. And so then kind of going into the observations and motivation for this work, we're really interested in, you probably heard about the TRAPPIST-1 system. We're interested in the TRAPPIST-1 system, which has 7, we think, rocky planets that, have pretty similar characteristics to our Earth, Venus, and Mars, like similar sizes and similar incident flux that they receive from the host star. And then we're interested in observing these planets, and interestingly enough, we're able to start pushing into observing some of these closer planets. And these are 2 exoplanets right here that are crossed out. Those are 2 exoplanets that have already been observed to have basically no atmosphere. So they're consistent with a bare rock, so we're really interested in like, how far does this push back into incident flux? So these TRAPPIST-1b and c is what we're currently going to be able to observe with JWST. So I'll talk more about that, but just it all depends on the different characters of the star and the gravity of the host planet, but that's what we're really interested in modeling here and comparing to observations. So what I'm trying to do is attack it from the simulation side to see, if we can constrain some of the properties of the planet, then what can we say about what the atmosphere might look like, or if we know something about the atmosphere, what can we say about the planet? So the 2 main processes that we think affect these planets' atmospheres are the geological process of the interior that outgas CO2 to the atmosphere, and then of course the stars, radiation, and wind interacting with the atmosphere to cause atmospheric escape. So I'm going to go into each of these a little bit more and just explain how we set these up in our simulations. So the first part, I'll talk about a little bit of background on like the geological processes that we're modeling here. So there's a few different tectonic modes that can happen on planets. You know, we hear about Earth has plate tectonics where, you know, you have core mantle lithosphere, but mantle convex, and as mantle convex, so does Earth, so that the lithosphere and the crust actually subducts into the mantle and gets recycled. So, but we actually see that other planets like Venus and Mars, they have what's called a stagnant lid tectonic mode, where you have a completely rigid lithosphere that doesn't move. So you don't have the subduction happening, and you still do have volcanic outgassing. So you have these plumes that occur when you when convection happens that still transport heat and material to the surface, but the lithosphere is rigid. And another way that we set this up, of course, as the mantle is convecting, transports heat, so the temperature of the mantle decreases over time, and that's what we're kind of basing our model on, which is from, I don't have it written here, but it's Brad Foley, 2018, Foley and Smythe, so that's the code that we're basing this on. And then I want to just kind of explain what this is. So Earth has the geological carbon cycle. This is what kind of is connected to the mantle convection, what kind of goes into releasing CO2 in the atmosphere, regulating CO2, and recycling CO2 back into the interior. So so the Earth has volcanic outgassing, which, you know, it's released to the atmosphere, equilibrates with the ocean, and then you have continental weathering on the mountains that then weather CO2 along with seafloor weathering. There's some weatherable rock on the seafloor that basically returns CO2 to the crust, which then gets subducted and then can return back to the cycle. Now on stagnant lids, which we think this is what is common. If it's common in the solar system, we're just going to assume that this is what is common in exoplanets as far as we know. So actually what happens here is you don't have subduction, so you don't have mountain building, so your continental weathering is extremely limited. And then we take it a step further with what we're modeling with the closer in planets that we're able to access with telescopes right now. And then we say, okay, well, actually, these oceans have probably completely evaporated. So then what we're left with is just basically CO2 is not recycled. All the CO2, it was originally in the interior, it gets outgassed, it doesn't go back in, it just stays in the atmosphere or gets atmospherically escaped. So that's what we're setting up for our picture. It's a one-way street to go to the atmosphere. But then in the code, and there's a lot of equations that go into this, we're interested in what controls outgassing the most. So two biggest things that control the outgassing are the carbon budget. So that's how much carbon is initially in the mantle to start out with, and the radiogenic heat producing element budget, which is that's like uranium, thorium, potassium. Those are the things that heat the mantle and allow outgassing to continue for as long as it does. And then I just showed here, like, these are two different 10 to the 20 mole carbon budget and 10 to the 22 mole, and you see how high the outgassing rate is over the time that it lasts between these two cases. So that's the side of our simulations that produces CO2 into the atmosphere. Now I want to go into what can take CO2 out of the atmosphere. So there's a lot of different mechanisms of atmospheric escape that can occur. And spent a lot of time over the last year and a half kind of just like exploring what the different and then what the dominant processes are. So we started out with like a common estimation that many people use in the literature today. So it's called energy limited escape, where you basically just set the incoming stellar rate of energy equal to the energy gain of the atmospheric material. And what it ends up being is just your XUV, which is your high energy flux, is really proportional to how much you lose. So it's a pretty simple and very rough estimation. So we were like, okay, we can try to make it a little bit more detailed. James escape is just the loss of, the high velocity, high altitude, light atmospheric constituents. So we implemented for a simple CO2 atmosphere, which then we think, can get split up into different things like oxygen, ions, and that kind of stuff. How much can be lost from this James escape? And what it depends on is the exospheric temperature. So that's where the exosphere is where things can be lost by James escape. Which also depends on the star coming in. But what we found actually is that even for a very light gas like atomic oxygen, you need extremely high exospheric temperatures to cause any appreciable amount of escape. So what we ended up including for atmospheric escape were these more in-depth MHD, magnetohydrodynamic simulations that were done by this group done in all 2018 to really actually model the stellar wind. So from our simulations and from this work, it's likely that the stellar winds have big impact on the atmosphere. So they were able to model all these specific things like the velocity of the wind, pressure at the planet's orbits, and the number density of particles. So what they're able to do is, so stellar wind can basically blow off the ions high up in the atmosphere of these planets. So they're able to do these very complicated simulations, which have been thoroughly tested on solar system planets like Venus and Mars. So they're based on the Venus and Mars composition of CO2. And then they're able to calculate exactly what the ion escape rate is. So we can get how much mass is being lost directly from this. So this is what we ended up using. And the great thing actually is that what they found is you can actually model this with a scaling relation, which stellar wind depends on the mass loss rate of the star. So that's what's there. And so it's directly, the atmospheric mass loss rate is directly proportional to the stellar mass loss rate. The paper that I showed, they cite a stellar mass loss rate of 2.6 × 10⁻¹1, which then produces a constant atmospheric loss rate of 57 kilograms per second. But there's actually a previous paper which cites a value which is almost an order of magnitude higher, which means it's not as constrained as we'd like it to be, but we're going to test these different stellar mass loss rates, and it's good that we have the scaling relation to be able to do that. So then that produces atmospheric mass loss rate that's even higher. But then we went a little bit more into the literature of like, there's actually been work done to connect age of the star, the rotation period, to the X-ray luminosity, then to the stellar mass loss rate, which have error bars for all these, but thought it was a good idea to not just assume a constant loss rate to we know that these stars are changing over time. They're more active in their early lifetime, and then they spin down over time and become less active. So what this means is we can then model this as a function of time. So then this is just showing how actually the atmospheric mass loss rate varies as a function of age for this variable case, and we use all three of these cases. So this is specifically for TRAPPIST-1c, because that is what we're really interested in. So I'm going to get more into that now. So TRAPPIST-1c is this planet that I showed on a previous slide, but and that its incident flux is 2 times that of what Earth receives. So it's and its mass and radius are kind of Earth-like. And then we're like, this kind of looks like Venus in terms of its incident flux. So we think if it's CO2 dominated, maybe it would have a very thick CO2 dominated atmosphere. I did my own simulations of this specific planet, and I did almost over 2 million simulations varying both this loss rate and then 4 different geological parameters, 2 which I already talked about, and 2 manifold reference viscosity and initial natural temperature that also are important. They don't affect the results as much, but they're still unconstrained, so it's important to include those. And you can see here, this is, atmospheric size, PCO2, those are the same thing. So you can see how the atmospheric size just kind of can go down over time depending on these loss rates and how much CO2 you start out with. That's the biggest thing, is how much carbon you start out with inside the planet. And then given that the PCO2 is less than 0.01 bar, so assuming little to no atmosphere, these are our successful simulations. So we see these two parameters don't have a big effect. This does push our heat budget scales more likely to have small heat budget scales, but what it really constrains is CE total. So this carbon budget that we start out with, it's of course dependent on the loss rates, but it's interesting to see that in all of these cases, it constrains it somewhere, which is actually, we think an estimate for Earth's initial was 10 to the 22. So it definitely constrains it to less than what Earth started out with. So can't, say for sure about anything, but you can say that, if in any of these cases, it does seem to be, somewhat volatile core compared to Earth. But of course, more work needs to be done. And one thing I just did kind of for like more of a future reference, I thought it'd be interesting, given if we know any two of, loss rate, carbon budget, or the PCO2 value, like you might be able to constrain one of the other ones. So this is just showing like if you have a constant loss rate and here's your carbon budget, like you could find on here what your PCO2 value might be, or if we assume the variable atmospheric loss rate, which I showed, and this is just like the reference loss rate at the current age, then what do you expect to end up with? And of course, there's like a lot more that can be done with this to like learn more about these planets and just to better understand them. So, theoretical things like better understanding the stellar winds, and how the stars spin down over time, and how that is all connected. Of course, understanding the details about atmospheric escape is a very complicated problem. And obviously understanding, it's hard, you can't really observe what's going on inside of these planets, but better modeling the physical processes that are happening. Observational, there's been limits on what we can observe for dwarfs, but there are, some proposals for observations that will get at more of this like high energy radiation and stellar winds that we're interested in learning about. Also the ages of dwarfs. The age that's cited for TRAPPIST-1 is 7.6 gigayears, but there's error bars about 2.2 gigayears on that. So just better constraining those things. There's going to be, or the team has proposed for more observations of TRAPPIST-1c to see, what actually, what composition the atmosphere does have and how much of the atmosphere it has. And then finally, one interesting thing is the uranium and thorium, the radiogenic heat producing elements. If you could connect those to the stellar abundances of the host star, you might be able to get at how much of those would have started inside the planet as well to kind of constrain that parameter a little bit better, which would be helpful. But yeah, that's what I have for today. I just wanted to thank these people who have helped me, and then the Center for Planetary System Habitability for funding me. Yeah. I'll take that.
So we do have couple of minutes for questions, and if anyone online has a question, feel free to raise your hand or post it in the chat. So Tim, we'll go ahead and start with you. You already raised your hand.
Hey, can y'all hear me?
Yep.
Mm-hmm.
Okay. Yeah, I had a question about your initial carbon cycling model. Mostly about the sort of continental weathering and geologic sequestration of carbon. Because I guess to me the bigger factor on whether that happens is not plate tectonics, but is availability of liquid water. And so as a sort of counter example, like Mars has the potential for having a geologically significant sequestered carbon reservoir in carbonate bedrock across the planet. And as you rightly point out, Mars is, stagnant lid. So like, is there any possibility to input into your model some simple empirical relationship for geologic sequestration of carbon, dependent on, I don't know, like surface temperature or water fluid water availability?
Yeah, actually, so the model that we started out with actually does account for the geologic sequestration through seafloor weathering. That's what the model assumes is the dominant process of weathering on these stagnant lid planets. All we did was basically turn that off for these planets that we think don't have liquid water, if that makes sense. So yeah, our model can account for, or Brad Foley's model can account for that.
And just out of curiosity, because this is like totally outside of my area, I'm just curious, like, how big a factor is that when you turn it on or off? Like, what, does it change the carbon CO2 buildup by like order of magnitude, or is it like factor of a few or something?
Well, usually it depends on how much weatherable rock you have, which you usually reach a limit to how much you can weather based on just, you have this crust, but since it's not being recycled, you reach this limit where you can't weather anymore, and then it's only outgassing again. So it doesn't play as big of a role.
It's super interesting. I'll leave it to others. There's other processes of geologic overturn, like impact cratering, that could expose fresh rock. That would be super interesting to think about. But this is really interesting stuff.
Thank you.
Anyone in the room have a quick question? Otherwise, we got one more online.
I'm trying to remember all the different planets in the TRAPPIST-1 system.
Yeah.
And whether there be one of the other planets might be an interesting contrast to this one, say being cooler, and thus could retain the water over a longer time period.
Yeah, because this one's TRAPPIST-1c. I mean, there's all the other ones, other than V, are like a lot further out. I think trying to remember which one. It might be G, which there's ones that are a lot cooler. If I go back to that plot of incident flux, you have these other planets that are right around where Earth is. So it's very possible that if TRAPPIST-1c doesn't have an atmosphere, that doesn't mean the rest of them don't, right?
It'd be an interesting contrast.
Yeah.
All right, well, thank you very much. I think we need to move on to the next speaker. You did have one person online. They may be able to ask their question in the chat and you can answer it there.
Cool.
All right. I'll go ahead and pull up the next presentation. All right, our next speaker is Jialong Ren. His research interests are in fluid and solid mechanics and numeric simulations with interests in planetary science. There are two projects currently in process. One is the fragmentation and reassembly into rubble piles of planetesimals, and then also compaction and differentiation of small ocean worlds such as Ceres. So thank you very much for speaking.
Hi, I'm Jialong. So first, I want to thank my collaborator, as well as Teixeira and also Mohit Wendy from JWST. So this talk is formed by 3 parts. First is about the briefly motivation and the backgrounds, followed by the compaction of series. Start with comparison with 2 different approaches used by previous works and this work, and also finally show a simulation, more complicated simulation of series compaction. And finally, I will talk about the deep or synchronization process and what's the primary results coupled with synchronization with compaction. So here is the basic information about series. It's the largest body in the asteroid belt, and the orbit is at about 3 AU, and it's due to its bulk density. Like 25% series is in water by mass. So it also makes a most water-rich body in the inner solar system. And also the Dawn mission shows some very interesting observations like carbonates and also spores of organics. And we all know that the habitability rely on this triangle: water, shelves, and energy. And the Dawn mission also revealed the evidence of recent and possibility ongoing geologic activities. The most notable one is the Ahuna Mons. It's the tallest mountain on Ceres, and it's a recent or still active pearl volcano. Now, if we look deeper into Ceres, whether the rocky core of Ceres is porous make a big difference. So, porous rocky core supported the energy and the elements transportation through its history, and also provided a platform of an interesting platform whenever Ceres is triggered by local events such as a huge impact. And we have motivation on these 2 levels. First, Ceres itself is recent interesting because it's a recent or possibly still alive. And the second level is Ceres is a representative of volatile rich bodies in our inner solar system, and also possibility in other systems. So next question is, what do we know so far about the Ceres interior? After the Dawn mission, Boga anomaly is measured, and Carcadell calculated the normalized moment of inertia of Ceres is value 0.37. However, like a density or porosity profile is not unique under this constraint. For example, a 2-layer model or 3-layer model with a denser crust would all match this value of 0.37. But we know that Ceres is at least partially differentiated. And from another set of approach, there were many thermal and also dynamic models on Ceres. In this model developed by Newman et al., the rock phase, ice, liquid water, and also void space are all considered. And they were heated by the radioactive isotopes. With this heated, ice was melted, and rock is warm and soft. In all scenarios, they investigated fully compacted rocky core form at the last stage, suggesting that compaction efficiently eliminates the porosity in the rocky core in the interior. And this is a modeling work from another group, the real. They also use this hot pricing as our creep flow as their primary mechanism. However, by considering this core cracking process, they could remain or reintroduce some porosity into the interior. And here comes to the question and bring me to the next part. What if porosity has never been lost in the first place? Yes, I'm typing something. So let me first explain some basic concepts. This cartoon shows the two-phase flow phase that we are interested in. So in this two-phase flow phase, different from the hot rising, the stream rate is constrained, or is driven not only by the solid or isostatic pressure, but by the difference between fluid pressure and solid pressure. We call it over pressure. And in the other side, the porous flow, the fluid flow, is governed by this Darcy equation, or Darcy's law. And as the flow is initiated, steeper pressure or steeper fluid pressure gradient develops to generate the, because like if you want to have a flux, you need a larger gradient of fluid pressure. And those black arrows are just conceptual. We are not going to say gradual approaching from the fluid pressure change from this static to the isostatic pressure. It's just having the instantaneous. Can't use this. Let's use this. And here is a very simple case. One-dimensional planar compaction. This region is 100 kilometers high, and the gravity is uniform as 0.2, like a typical gravity inside of the cells. I can play my computer later, but let me try to finish the talk rapidly. So we have this one. To further quantify it, we introduce this term called the convection degree. It's generally developed or describe the degree of convection. So the blue line is for the one-phase case called pricing, and the red line is for the two-phase case. Right? Convection with porous flow. We can say that the one-phase case is much faster than this convection with porous flow, and we also plotted a log time scale. So the convection with a two-phase convection itself is slows down. It's getting slower and slower. Also, when we move to a spherical geometry, it's also like the hot pricing is also much faster than the two-phase flow. And it's interesting to say that maybe I'll connect my computer later. The porosity of this spherical geometry, inside porosity, they moves uniformly with time, and like they decrease uniformly. It could be explained with such simple analysis. I won't follow it line by line, but it generally told us that due to the inverse square law of gravity and also this spherical geometry, if we started with a uniform pressure, then the time derivative of pressure for the rocky part, for the rocky core part, is a constant. For like war is unchanged with the radius. So we will always have this uniform porosity inside of this rocky core. And gradually we have a stable figure here. And in this page, we move to more realistic convection of series coupled with a thermal model. So here we use some dimensionless values to better understand and also describe this phenomenon. One is the convection length, and the other is the convection time. So here is two different temperature, 200 Kelvin and also 800 Kelvin. The convection time, like the time scale of convection, is very different from this 1.7 times 10 to the 24 million years for this cold situation and only 5 million years for this hot situation. And here we are looking at temperature contour, the volume fraction of free water, volume fraction of ice. The summation of those two is the porosity, the term porosity we use here. And finally is the relative flux of fluid to solid, or like water to rock. And when this relative flux comes to zero, the convection is essentially stops. So this shows the convection of like the same case with this figure. And here we move to the desynchronization. So those those are two representative typical reactions of synchronization, and our collaborator Mohit simplified them and provided this database for phase diagrams to us. And we just choose one homogeneous value from the pressure condition, mean pressure of 60 megapascal, and we just pick this pressure point and choose the corresponding properties like reaction temperature and the heat capacity for both phases. Now here is the phase diagram we are using. Like we consider those phases like a dry rock, which is all wind plus water when this temperature is all very high. So we didn't consider the critical point behavior of water yet. So we always treat it as room temperature water, which is not real, but could be modified later. And when it's cold, we have a combination of dry rock and serpentinite and also water. So within this triangle in the middle, the temperature is the same. If we look at it, the temperature is a constant. And also when it drops down, we have like different branches of dry rock with serpentinization or serpentinite with ice. So with a thermal model, the one location's property could move vertically, like a high temperature and high pressure. And also with a dynamic model, like the property with a certain location or radius could also move horizontally with the change of water composition by convection or upward flow. And here is if we ignore all those mass transport but only focus on energy transport, we'll have two situations by considering ice melting and also serpentinization or ice melting only. So in this figure, the ice melting and serpentinization or serpentinization acts as a buffer to slow down or storage more energy to keep the peak temperature in the later stage higher. But what will happen if we also consider the convection is different? It's like the serpentinization will move the water with a high enthalpy and heat capacity to the surface and accelerate the cooling process. So we have another primary preliminary results I can show later in this method. I'll just go to the conclusion. So the basic story is this: the pressure gradient required to expel the pore fluid together with the permeability as a very strong function of porosity. Usually this number is 3, significantly slow down the convection of the rocky core. And the series may not have enough time to fully compact this rocky core when it's still warm and soft, left some porosity in the interior. And therefore, the interior of a series could still be porous, but it would also be affected by serpentinization process or deserpentinization process. And that's to thank the Center of System of Planetary Habitability to support the funding me. Do I have time to connect to my own computer?
Yes, you do. The speaker will connect their computer and then show the videos. These things open up soon.
Yes. Sync. Yes, there is this. Oh, I need to send. It's very.
Like technology.
That how the unit result
A lot of power.
Yeah. This is the possibility of getting.
Anticipation.
You may ask me some question, and I was thinking about it when I'm doing this. It won't take too long. It's fast, but it actually consumes.
All the questions in the chat so far.
Yes.
It's like Rami's got her hand up. Yeah. Yeah, Rami, go ahead, while the speaker's pulling up their Zoom.
Okay, thanks. Can you hear me?
Yeah.
That was a great presentation. I was wondering, so what you're modeling here, how is it related, or would it be modified by the fact that that series may be partially differentiated?
So actually, this is a result of partially differentiated, like the dehydration degree could be fully dehydrated at the peak temperature point, or I mean, like recorded. So maybe I can first play the animation first and get a better. Thank you for the question. I'm just share screen. I'll just jump to the interesting series simulation. So this is for convection only, but coupled with thermal, not only thermal, not the synchronization. So here we are looking at the temperature profile, porosity, and the overpressure in a unit of megapascal. So we can see here the temperature first increase and then decrease. And when the temperature is hot enough, the porosity could evolve and the flux would go upward. And when it's finally the temperature is low enough, the convection stops. And there's a local minimum or choke here is due to the interaction of this convection and the upward flow. And like finally, the overpressure is essentially the isostatical stress pressure, because like the fluids, the flow depth, we do not need any other fluid pressure gradient to expel those flow. It just stay there. And so I think this is, to me, is partially differentiated. And we move to this one. So in this one, what's different is we consider the both phase changes as melting and the synchronization. So temperature profile, temperature and velocity are the same, but what's shown on the left is the degree of hydration. So when it's 1, the all available Loki phase is 29, and when it's 0, the all available Loki phase is all. Why I say available, because with some expel of fluid, maybe the already dehydrated part may not have enough water to be rehydrated or to be hydrated. So like that, we will have some cold order at the end phase, and for in this bottom or center area. So I think maybe it's time for questions. I won't share the sample.
We have a couple minutes for any other questions anyone may have.
Did Romy's question get asked and answered?
I believe he did during the video, yes, that he thought it was partially.
If I play this, blue is 1 phase, red is 2 phase, and this green and black is only for this 2 phase. The interesting case we derived. So if we play it again, that at the beginning, the compaction, this full display only happened at this boundary layer at the bottom, and accelerated those fluid before it's too cold. Or this is not too cold, this is just stopped. Temperature is not equal, and this is for spherical, similar, but a little different. You can say that there is a huge time or speed difference between 1 phase case and 2 phase case. Here is the uniform movement or like uniform decrease of porosity I'm talking about here. I'm ready for other questions.
Any other questions? All right, well, thank you very much for your interesting talk. All right, thank you, everyone. That is it for our 2 presenters, and I believe our next seminar is in a couple of weeks. So be sure to take a look at your email for that announcement.